So today we're going to start looking at the truly physical part of physics, the stuff that you can actually see happening. Okay, we're going to start describing the motion of objects and systems. Okay, things like that. So what we're going to look at in particular is two different ways of looking at motion. Okay, those two different ways to look at motion are scalar and vector. Okay, and they look at the same trick, but they do it from different points of view. Okay? Now, the example I always use is a Star Wars example because, as you know, I'm a nerd, and so everything would go back to something like that. Okay? But back in the original trilogy, Luke was told that Darth Vader betrayed and murdered his father, even though Darth Vader was his father. Spoiler alert, in case you didn't know that. Okay? Darth Vader was his father, okay? But it was explained to him that what he was told was true from a certain point of view. Because when his father became Darth Vader, the good man who was his father was destroyed. It was true from a certain point of view. Well, when we look at scalars and vectors, we can look at the same trick from 2 points of view and see two things that, while on the surface are the same, might be very different when we start looking into them in more detail. Okay? So, the first thing that we have to get past when we start this part of the unit is that the way we talk about distance and speed and time in North American society is really fouled up. Okay, let me give you an example. If I was to ask you how far it is to Edmonton, what would you say? 3.5 hours, right? That's what everybody's thinking. Do you know how often I've gotten the correct answer in 23 years of teaching to that question?
Once.
Twice. And that's not just 23 years, that's like at least twice a semester, so that's 4 times a year. For 23 years, I've had the correct answer twice. What did I ask?
How many minutes?
I asked how far it is to Edmonton. And what did we all think? How long it would take to get there. Because the way we think about distance in North American society is messed up. Okay? When someone asks how far something is, we naturally think they want to know how long it will take to get there. Because that's probably what they want to know. Okay? That's not right. If they ask you how far it is, you should tell them it's 320 kilometers. Because that's how far it is. Unless the North American continent splits open in between here and Edmonton, it's always going to be 320 kilometers. Does it always take 3 hours? That's the problem. We tell them 3 hours. I can tell you that it can take anywhere between 2 hours, I'm not proud of that, okay, or 9. It all depends on the weather and the crazy person behind the wheel. Okay, if you have that crazy friend, yeah, like by the time I got there, I was white as a ghost and just wanted to puke my guts out and kiss the ground. Okay, because yeah, my friend was very, very crazy. Okay, and then there was a snowstorm when we came back from a field trip to Edmonton, and it took us 9 hours to get home because they closed the road. We had to take all the secondary highways back. Okay, yeah, 3.5 hours is not how long it takes to get to Edmonton, because how long it takes to Edmonton is dependent on 2 things. One of which can't change, how far it is to Edmonton, and how fast we go, which totally can change. Okay? I mean, from day to day, it takes you a different amount of time to get from one end of Calgary to the other. That can vary by 45 minutes to an hour. Okay? Sometimes you can get right through on Deerfoot and you're done in 35 minutes. Okay? And other days, like the other day, it can take you an hour and a half. Okay? So we don't want to tell people when they ask how far something is, we don't want to tell them how long, okay? Especially in physics. Okay? In physics, if a question says how far, they want to know how far in kilometers or meters or centimeters or some measure of distance. Okay? They definitely don't want a time. If they want a time, they'll ask how long, and that means give them a time in seconds or hours or days or whatever it happens to be. Okay, everybody with me there? It's a habit we have to break because it's a habit we all have. okay? Even myself, I still do it, okay? And I let other people do it to me, okay? I'll give you an example. A buddy and I went backpacking in Kootenai National Park one summer, and we had a really long, like 33-kilometer day, 2 passes. It was hellish. And we were not where we thought we should be. It was like 6 o'clock already in the afternoon, and we're like, okay, we're out of water, hungry, and we might be lost. So we sat down, we're poring over the map, and all of a sudden this guy wearing army fatigues comes bebopping uphill, like, and I mean like he's running, with a big pack, probably weighed 65 to 70 pounds, running uphill towards us. And we're like, oh, dude, do you know, did you come from Tumbling Creek campground? Like, we're looking for Tumbling Creek, we think we might be lost. He goes, no mate, it's just down the trail there, it's like 10 minutes. We're like, oh, thanks man. An hour later, we stumble into that campground because we're 2 out-of-shape teachers on their summer vacation who are dead exhausted. We're not the Australian Special Forces guy who's out for an afternoon jog with his heavy pack, okay? But what did we do? We asked him how far, and he told us how long it took Superman to run uphill with a 70-pound pack to that point. Okay, so I mean, when we got to that camp, we were making plans on how we were going to hunt that guy down. It was all his fault, right? And then we got some food and water, and I turned to my buddy, he's also a physics teacher. And I said, Sean, we must never speak of this again. But do you realize what we just did? He's like, shut up. We let that guy tell us how long it was when we wanted to know how far it was. It can get you in real trouble. Okay? So we got to make sure it's a habit we got to break. All right, so we got to differentiate between distance and displacement. These are similar measures, but they have one difference. One is scalar and one is vector. Okay? Speed and velocity have a similar relationship. Up until now, you probably use those terms interchangeably. Right? Speed and velocity mean the same thing. They mean how fast you're going. Except they don't. You ever see a velocity limit sign? There's a reason for that. Velocity is a vector quantity. It has magnitude, that means how big or how fast, and direction. So if there was ever a velocity limit sign, it would say 100 kilometers per hour north. Okay, everyone follow me there? Okay, so like if you ever get pulled over by the police and the police officer comes up and asks you, do you know how fast you're going? So that's usually what they ask you. Hey, you know how fast you're going? Tell them your speed, that's what they want to know. Don't tell them your velocity. If you do, you'll find yourself on the side of the road undergoing a field sobriety test. Okay, because they're going to think there's something the matter with you. Okay? When they ask you how fast you're going, they expect 140 kilometers an hour, officer, I'm really sorry. Not 135 kilometers at 10 degrees south of west. Okay? Because that's going to have a follow-up question. And how much have you had to drink today, sir? Okay? Because that's not the same thing. Velocity and speed are not the same thing. Speed is how fast are you going, not caring what direction. Velocity cares what direction you're going. Okay? Distance and displacement, same relationship. Okay? Distance is scalar. It's just how far. Okay? If I walked back and forth across this classroom, okay, I could rack up a kilometer of a distance or a distance of a kilometer if I did it enough times. But if I end up back where I started, my displacement would be 0. Displacement measures how far and in what direction I end up from where I started, not how far I went. Okay? Distance cares how far did you go. Displacement cares how far did you end up from where you started. Okay? And in what direction. You follow the difference? Okay. All right, and then we're going to solve problems related to motion, and we're going to use some formulas that hopefully you still have, because they're on the back of your periodic table. Okay, so now we're going to use the other side of the periodic table. Okay, in this unit, we're going to use all those formulas that are on. Okay, so we're going to use this formula, and that formula. And no, I am not crazy. Those are different formulas. Okay? This formula says that speed is distance over time. It's scalar. All the quantities in it don't have direction. This one says velocity is displacement divided by time. The little arrows over top of the V and the D indicate that those are vector quantities that not only have a magnitude, but a direction as well. Just so you don't get confused which ones go with which. Okay, everybody all right with that so far? Okay, so like I say, you're gonna need that periodic table out, not much today, but like for the rest of the unit. Make sure you locate it between now and like tomorrow. Okay, so if you've ever gone hiking off trail, done any orienteering, you know that how we describe travel in everyday life is only effective at getting you hopelessly lost in a roadless or trackless environment. Okay, if you're not from around here, okay, and you say to somebody, you know, how far is it to High River? And they tell you it's 25 minutes. Are you screwed? You're, like, I mean, unless you can read signs, and then why'd you ask for directions in the first place? Okay, you're cooked because you don't know even what direction to go in. And 25 minutes, am I walking? Am I flying? Am I driving? It makes kind of a difference. I can't walk nearly as far in 25 minutes as I can drive. Okay, that's a completely useless way to describe to me how far High River is from here. Okay? Now, if somebody said it's 25 minutes south of here, I'd have a much better chance of getting there. Okay, that's still not a great way to describe it, but at least I'd know what direction to go in. Okay, I probably still wouldn't end up there because I could pick the wrong mode of transportation. Okay, if they said it's 18 kilometers at 10 degrees east of south from here, I'd have a really good chance of finding it then. Okay, because then I'd know how far and in what direction to go. Okay, and then my mode of transportation wouldn't make any difference. Okay, everyone all right with that idea? Okay, now, does that mean that giving somebody a scalar description is always worse? So let's say the person asking got these answers instead. It's 18 kilometers from here. It's 18 kilometers at 10 degrees east of south from here. Okay, is one of those answers better than the other? I mean, one answer has more information, it has a direction, but given that there's a vast series of interconnected roads existing in this area, it probably wouldn't be hard to figure out that 18 kilometers would mean I go that way along the road and I follow the signs. I could probably still get there. Okay? There's sometimes where a scalar description is more adequate or preferable to a vector description. So let me give you an example. Let's say I'm looking at this map here. Actually, I'm not looking at this map. I'm actually standing right here at Seldom Inn Campground. And I'm headed to Snake Indian Falls Campground. Okay? Right outside of Seldom Inn Campground is a sign. And that sign says Snake Indian Falls Campground, 27 kilometers. Now, is that a scalar description or a vector description? Scalar. It just said 27 kilometers. What is it assuming I'm going to do?
Take the trail.
Yeah, exactly. I'm going to follow this trail from Seldom Inn Campground to Snake Indian Falls Campground. in that situation, a scalar description is just fine. In fact, it's better than if the sign said, Snake Indian Falls Campground, 19.8 kilometers at 50 degrees west of north. Because if it said that, I gotta follow this line, which is fine if I have a helicopter. It's not great if I'm on foot because, well, there's all these rivers, the gray parts are glaciers, okay? So there's gonna be all manner of disaster in between these 2 points if I don't follow the trail, okay? So there's some situations where a vector description is appropriate, and there's some where a scalar description is appropriate, okay? If I'm a helicopter pilot, if I'm a cruise ship navigator, okay, then vector descriptions are what I would prefer because I'm not following roads or trails. I have to point my vessel in whatever direction and go that way. Does that make sense? I only bring that up because we sometimes get the idea that vector is always superior, okay? And it isn't. It always has an extra piece of information, but it's not always superior. It's very situational. All right, so if we say Calgary is 40 kilometers away, we make no reference to which direction Calgary is in. We just get on the road and we follow the signs. In that case, we've made a scalar description of where Calgary is. Okay? We have only said how far away it is, not what direction. Okay? So if I went to the Calgary Zoo, which is basically the center of Calgary, okay, and I use Google Maps, it would tell me it's 42.8 kilometers, so 40 is close. Okay? And it would take me about 30 minutes. Okay? Does Google do this same calculation all the time? It does. Okay? It does the calculation we just looked at. B equals D over T all the time. Okay? In fact, it recalculates it while you travel. Okay? If there's like an accident or something that happens on the road, it will recalculate the value. If it's significant, I found out the other day because it scared the tar out of me, okay, it will actually alert you. And it'll say, there's an accident on your route. Would you care to take a faster route? And I'm like, I'm driving. I don't want to be distracted. So no, I'll just go slow. Okay? But it will actually do that. And it calculates these using the same formula that we're going to use, okay, here in class today. All right, now, what Google assumes is that you're going to follow the road. Okay, that's why it doesn't really tell you which direction. It'll give you a general direction, but it won't give you compass directions. Okay, it's also why it's not all that good if you're not somewhere where there's roads that Google knows, okay, in order for you to follow. Okay, it's not really good when you're off trail. Okay, everyone all right with that? So that's a scalar description. And in this case, it's okay, because there's a route to follow. Okay? If there were no roads, that would really not be a good way to say it. Okay? Because we could go in how many different directions? Well, how many choices do we have if someone doesn't tell us which way to go? 360 choices. Right? You got 360 degrees in a circle. That's how many choices for what direction you have to go if somebody doesn't tell you which way to go. Okay? Now, well, I say more accurate. I should say more descriptive. I think I changed it in your notes package to say descriptive. A more descriptive description would be to say Calgary is 40 kilometers away on a vector 13 degrees east of north. Okay? Now I would get there regardless of whether I followed the road or not. Okay, that's a vector description. Okay. Doesn't make it any better or any worse. And the reason I took accurate out of there is because it isn't more accurate. Accuracy doesn't depend on whether I give you a direction or not. Accurate depends on how you measure it. Okay, so let me give you an example here. Okay, 40.01 kilometers, or 40 kilometers at 13 degrees east of north. Which one is more accurate?
Okay. 40 kilometers east of north, 13 degrees east of north.
Okay, that one's more descriptive. It has more information because it has magnitude and direction. But which one is more accurate?
40.01.
40.01. Accuracy depends on measurement, not whether or not you get extra information, okay? This is accurate to plus or minus 1 kilometer. According to that measurement, Calgary is somewhere between 39 and 41 kilometers from here at 13 degrees east of north. According to this measurement, this is plus or minus 10 meters. Okay, so that tells me that Calgary is somewhere between 39.99 and 40.00 and 40.02 kilometers. That's more accurate. Okay, so your accuracy depends on how you measure something, not whether or not you get a direction with it or not. Okay. Okay, now for us, most of the time, well, pretty much all the time, we're not going to use degrees and compass directions. If we use compass directions, it'll be like north and south, or east and west. We only ever deal with what we call one-dimensional motion. Okay, that means it can be described as either positive or negative. We don't ever bring in any trig in Science 10, simply because we don't know if you've done the trig unit in Math 10 or not. Okay? So if you took like science first semester with me, it's totally different than when people take a second semester. Way more people have taken math second semester than first semester. So I have to teach all that stuff, okay, in semester 1 that I don't have to for semester 2, because you guys are already familiar with it. Okay, but we don't do the trig, okay, in Science 10, so you don't have to worry about it. Okay, so if trig scared you, you don't have to worry about trig. But if trig scared you, it's the first thing I teach in Physics 20. Just putting it out there. All right. Well, let's look at this as an example. Let's say, for whatever reason, I'm going to walk from my house to Walmart. Okay? Now, unless I live right behind Walmart, which I don't, okay, I can't walk in a straight line from my house to Walmart, can I? I'd have to walk, like, well, through trees and houses and stuff, and that'd be kind of awkward. So I can't walk in a straight line. So I would, walk down my block and then turn onto another road and then, turn onto, Northridge Drive and go across the river and then, do this. Okay, I can't walk in a straight line, but I can do that. Let's say that when I get to Walmart, having followed this path, I've ended up walking 4 kilometers. Okay, is that a vector or a scalar quantity? Scalar. Doesn't have a direction. That's how far I walked. I walked in a lot of different directions along the path from my house to Walmart. Okay, that is just how far I had to walk. That is a distance, and it's a scalar quantity. Okay, now looking at this trip from a different point of view, from a vector point of view, it would look like this. Is that line 4 kilometers long? No, shortest route between 2 points is a straight line. So this is definitely shorter than 4 kilometers. Okay, and I can't remember if I picked a distance. Did I pick a distance? 2.8. Okay. All right, so we'll say that along that route, which we'll use black for, so that line is 2.8 kilometers at 38 degrees south of east. Vector or scalar? Vector. It has magnitude, 2.8 kilometers, and direction, 38 degrees south of east. Okay, so this is a displacement. That's d with the little arrow. Okay, that is how much I have changed my position. Okay. My initial position was home. My final position is Walmart, okay? And that involved me changing my position by 2.8 kilometers in a direction of 38 degrees south of west, or south of east, sorry. Okay, everyone all right with that? All right, let's say it took me a half an hour to walk to Walmart. Okay, so that is gonna be a time. How fast did I walk? Went 4 kilometers in half an hour. How fast would I have walked in an hour? Or how far, sorry, would I have walked in an hour? In an hour? 4 kilometers in half an hour. How far would I have walked in a whole hour? 8, right? If I walked 4 kilometers in half an hour, that means I walked at 8 kilometers per hour. Okay? How did I figure that out? I'm probably going to multiply it by 2. I did. This is actually what I did. I solved for my speed by dividing distance, 4 kilometers, by time. 0.5 hours. When you divide something by 0.5, you end up multiplying it by 2. Okay? Does everyone follow that if I walked 4 kilometers in half an hour, I'd walk 8 kilometers in an hour? Okay, so my speed, which is a scalar quantity, is 8 kilometers per hour. What's my velocity? That's trickier. The other formula that we looked at was this one. Velocity is displacement divided by time. Velocity is a vector quantity, displacement is a vector quantity. Okay? Now, I gotta do exactly the same thing. I just gotta plug in my numbers. So I'm gonna have 2.8 kilometers at 38 degrees south of east divided by 0.5 hours. Okay, so when I do that, I should get 5.6 kilometers per hour at 38 degrees south of east. Why did the direction stay? Is it okay that the direction of my velocity is the same as the direction of my displacement? It's absolutely necessary. Have you ever tried to end up east by walking north? You're not going to have very much luck with that. Okay? My displacement and my velocity have to have the same vector. They're happening at the same time. One is the result of the other. Okay? So my velocity and my displacement are always going to share a vector. Okay? The only way I end up at Walmart is if I walk at 5.6 kilometers per hour, 38 degrees south of east for a half an hour. So I end up 2.8 kilometers at 38 degrees south of east from my house, which happens to be the position of Walmart. Okay, everybody all right with that? This is the same trip from different points of view. Okay? Everyone follow that now? Okay, here's where it gets really weird. Well, this part's not weird. I get to Walmart and I realize I haven't brought my wallet. That's never happened, ever. Because I'm old and forgetful. That's why I put all that information in my phone. Now I have to forget both my phone and my wallet to be when I get there. Okay? So I get to Walmart and I realize I don't have my wallet. I'm not going to walk around Walmart for the fun of it. So I turn around and I walk the exact same route home. Half an hour later, I'm back at home. How far have I gone in total? Don't overthink it.
8 points.
8 kilometers. I walked exactly the same route home. If it was 4 kilometers to Walmart, it's 4 kilometers back. Okay? That means my total distance over the whole trip is 8 kilometers. It took me a half an hour to get home. Did I walk at the same speed? So my total speed for the whole trip was still 8 kilometers per hour, because that's what I did. I walked 8 kilometers in 1 hour. Okay, everybody all right with that? Okay, now here's where it gets weird. When I get home, what's my displacement? 0. Remember, my displacement is how much and in what direction I change my position by. My initial position was home. My final position was also home. So technically, I didn't displace myself. I didn't change my position. I walked 8 kilometers to accomplish. Okay? From a vector point of view, those two trips look very different. One says I walked 8 kilometers. The other says you didn't do anything. And it's the same trip. Okay? But they're both right. They're just looking at it from different points of view. Okay? So, if my total displacement when I get home is 0 kilometers, what's my average velocity over the whole trip? Keeping in mind this formula. 0. We just established my displacement, which is the d with the little arrow over top, is 0 when I get home. Well, 0 divided by anything is 0. Again, from a vector perspective, I haven't done anything. Okay? Your velocity is the rate at which you change your position. I didn't change my position, therefore I have no rate of change of that because it was 0. Okay? Everybody okay with that logic? Okay. Is time scalar or vector? It's scalar. Okay? Now, here's another thing we do totally wrong in North American society. Okay? Where do you live? I live 20 minutes south of here. Well, I just made time a vector quantity. 20 minutes south. That's not a thing, by the way. Okay? Time is not a vector quantity. Time does not travel south. It travels forward, as far as we know. Okay? We have only a linear perception of time, unless you have a time machine at home, in which case you're going to get really rich. Okay? Because people will pay to use that. But as far as we know, time only goes forward. Therefore, time is scalars. It can only get bigger. Scalar quantities can only get bigger. If I keep walking, my distance keeps getting bigger, even if I walk backwards. Okay? It's about how far did I go. Time is about how long did I do that for. Well, I can't make that shorter. Okay? Once I've walked that, I can't take it away. Okay? It's always going to be scalar. Time is scalar, distance is scalar, speed is scalar. Okay? Velocity and displacement are vectors, so they'll have a direction. All right, so this was all the stuff that we just did. Okay, so we'll skip over that. Okay, now before I get to this, I am going to give you a 3-minute break before I start talking about the mathy math. Okay? So one of the big things that's going to be super important in physics is algebra. Okay? We do a lot of like isolating a variable and manipulating formulas to solve for something. Okay? The extent to which we've done that so far in this course was to use the mole equation. N equals little m over big M, which is not like, real heavy lifting in terms of algebra, especially since we only had to manipulate it 2 ways. Okay? Well, with b equals d over t, we're going to have to manipulate it for v, for t, and for d. Okay? And we are not going to use, that was less dramatic than I wanted it to be, any of those, okay? Because triangles suck, and they don't help us with algebra, especially when we get to formulas that have more than 3 variables. Okay, so we just want to quickly review the rules of algebra here so that we have them. Okay, and that is, okay, rule number 1, to move a variable, you perform the opposite operation. All right, so if I'm dividing by something, I would multiply by it to move it to the other side. If I'm adding something, I would subtract it. If I'm already multiplying by something, I would divide by it, okay, in order to move it to the other side. Okay, the second rule of algebra, what you do to one side of an equation must be done to both sides. Okay, so if I multiply one side by t, I have to multiply the other side by t. Everybody okay with that? All right, and the third rule we haven't used yet, but we will. Okay, when solving for a variable, move what is not attached first. Okay, and attached means like directly against that particular variable. I'll show you what I mean here in a minute for that. Okay, when we are talking about v equals d over t, okay, right now obviously it solves for v. If I wanted to solve for d, what do I have to move? So d is already on top, which is where I want things if I'm going to solve for them. Okay, so I want to leave d where it is. What do I have to move?
The T beside B.
Right, I've got to move the t to the other side. In order to do that, okay, I just multiply both sides by it, which means I just bring it over here and it ends up beside v. Well, in order to do that, that makes it look kind of simple. But what I've done according to the rules is I've multiplied both sides by t. Right? So if I've got a t on the top and a t on the bottom, t divided by t is 1. So it makes it go away. Right? So I've multiplied that side by t. Now I need to multiply this side by t, which is why just dragging the t and putting it here is what works for the manipulation. Okay? But that's what it looks like if I'm following the rules of algebra strictly. Okay? Now, if I go back and I say, all right, I want to solve for t. What should I do? This is the trickier of the manipulations. Where is t right now? It's on the bottom. Can I solve for something if it's on the bottom? I can't. Okay, I'll be solving for 1 over that number, which is not the same thing. Okay, saying 1 over t is the same as t is saying that 1/2 is the same as 2. Okay, which we obviously know is not true. Okay, so if I want to solve for t, I first want to move t over to this side because now it's where? It's on top, right? There's nothing over it. Okay, so it's now on the top. I want t by itself, and right now I'm multiplying it by v. So what do I do with v? What's the opposite of multiply? Divide. Okay, so if I was going to do that, then I would simply, now v is over here. Okay, I've divided both sides by v, and now t is by itself. Right? Those are the rules of algebra. Those 3 rules will get you through any non-calculus based physics class. Okay? They got me through university. Okay? Those 3 rules got me through university physics because I didn't take any calculus based non-linear physics. Okay? Those 3 rules are all you need to manipulate any equation you might run into. Okay? So let's look at a different one that's got more than 3 variables. How many people have seen this formula before? Okay, took that in Math 10, I hope. Okay, that's the equation for a linear function on a graph. Right? So, this one will require us to use all 3 rules of algebra. I want to solve for m. Okay, so I want m by itself. What should I move first?
B.
Yeah, I should use b. I should move b. Why? It's not attached to m. X is attached to m. It's directly beside it. Okay? Directly under it is also attached to it. Okay, but because there's something in between and there's an addition operation here, this is not attached. So I'm going to move b over to this side first. How do I move b over to the other side? Minus, right, I subtract it. Okay, so if I go positive b minus b, it's gone because that equals 0. Okay, and then on this side I'll have y minus b. And then on this side, I'm left with m times x. Right? I want m by itself. What do I do with x? Just divide by it. Right? Right now I'm multiplying by x. Done. It really doesn't get a whole lot harder than that. We have a whole bunch of formulas that we're going to use in this unit. Okay? But like this might be the trickiest one. I want to solve for VF. What should I move first? What's not attached to it? T is not attached to it. Okay? There's a subtraction operation on the top. Those two numbers are attached. T is underneath that. I would do according to this formula, I'd figure out what the top was before I divided by the bottom. Hello. Hey. Sure. Santi, Mr. Dorsauer wants to do your registration. Okay, so I should move T first because it's not attached to VF. How do I move T? I'm dividing by T right now, so I should times. I should multiply. Okay, so multiply. T goes away on that side. T comes over to this side because what I do to one, I do to the other. Okay, now I've got T times A equals VF minus VI. I want VF. What do I do with VI? Yeah, add it to both sides. Okay, if I add VI here, VI goes away. Boom, I'm solving for VF. Okay, those three rules will help you manipulate any formula you can imagine, even going as far as something like this that you might do in Physics 20. I want to solve for M1. What should I move first?
R2.
Yep, I should move r squared. Okay, right now I'm dividing by r squared. So if I want to move it, I should multiply, right? Okay, so I multiply this side by r squared. Boom, boom. What's r times r squared? Got to think a little bit of math 10 here. By multiplying, I do what with the exponents? Add them. Okay, so r times r squared is r cubed. Okay. Okay, and then I want to get m1 by itself. What do I do with these two numbers? Right now I'm multiplying those three. What do I do with m2 and g? Divide them. Okay, so big G will go there. M2 will go here. Look, there's M2 and M2. M2 is gone. Okay, I've just solved for M1. And I didn't do anything different than we did with B equals D over T. It doesn't matter how hairy those equations get. Those three rules will always work. Okay? Does it take a little bit of practice? Yes. Okay? You gotta work your algebra muscles a little bit, okay, in order to get them in shape, but it's nothing overly taxing. Okay? Trust me, I've been helping my own son with Math 10. This is nothing compared to what you guys do in Math 10. I gave up. I gave him a tutor. Yeah. I mean, I could do the factoring, but I couldn't tell him what I did when I was done. I admire you guys for doing that stuff. Okay. All right. So, we're talking about the rules of algebra. Okay, I want you to write this one down. Okay, simple B equals D over T question. How far will a deer running at 15 meters per second travel in 45 seconds? first thing we want to do, just like when we did the mole equation questions, is write down our givens. What does the question tell us? Okay, first says how far. What do they want us to solve for? Distance. Yeah, distance is how far. If it said how far, and in what direction, then I'd be looking for displacement. Okay. All right, so I'm looking for distance. It says the deer is running at 15 meters per second. What did they give me there? Speed, yeah. Speed can be in meters per second, kilometers per hour, light years per century, whatever. As long as it's a distance and a time, okay, it's going to be units per speed. All right, so in this case, we've got 15 meters per second. Okay, and then 45 seconds. What did they give us there? Time. Now, something you have to watch out for, because sometimes it'll happen. Your units in the speed have to match your units for distance and time. If they gave me the distance in kilometers and the time in meters per second, I'd have to convert the distance to meters. My units have to match. Okay? Otherwise, I'm dividing apples by oranges, and it's not going to work. Okay? All right, so I'm looking for D. Obviously, this is the formula I'm going to use because those are the things I have. Right? That's actually one of the challenges in this unit is you've got all these formulas to choose from. You have to figure out which one to use. That's why we give you a mark for writing down your givens. By writing down your givens, figuring out which formula to use is like which of these things is like what I have. Okay? And it's pretty easy to figure out which formula to use. All right, I'm trying to solve for D. So what do I have to do with T? I get D by itself. Where does T have to go? I have to multiply both sides. Okay, so T's gone there, T comes over here. All right, time times speed. All right, well that makes sense. If I'm trying to figure out how far I go, and if I'm going 15 meters per second for 45 seconds, multiplying those two things together should tell me how far I go. Okay, so I'll take my 45 seconds, I'll multiply it by 15 meters per second, and that will give me my total distance traveled. All right, so this deer is going to run 675 meters in 45 seconds. How did I know my units would be meters?
Speed.
It's in the speed, okay? That's usually what we measure distance in, right? It's either going to be meters or centimeters or kilometers or something with meters on it. Okay, but here's the other thing. If I'm ever in doubt as to what my units should be, just put the units in here and do exactly the same operation. Seconds times meters per second. Okay, well, the seconds cancel and I'm left with meters. Right? So if you ever want to double check whether you've done your math right, check that you get the right units. If you get the right units, then you did the algebra right. All right, does that one make sense to everybody? Okay, try that one. How long will it take a tortoise to crawl 200 meters at a speed of 0.25 meters per second? Okay, so they're asking us how long it'll take. What are they asking for? Time. Okay. Right, and they tell us 200 meters. That would be a distance. If it was a displacement, what else would there be? A direction, 200 meters forward or south or towards the beach, or whatever. Okay, and then at a speed of, so that's a dead giveaway. They told us it's speed. Okay. Hello. Hey. Yep. Here. This is Baxter wants to give you registration. Okay, 0.25 meters per second. Okay, if I can't tell, if they don't say at this speed, I have to go by the units to determine what it is. If it's in meters, it's distance. If it's any time unit, hours, seconds, whatever, okay, then it's time. All right, so I'm looking for time. Okay, I can't solve for time on the bottom, so I need to move it to the other side by multiplying both sides by it. And then what do I have to do with V? Right, divide both sides by, move it under. Okay, so t equals 200 divided by 0.25, that should be 800, right?
Mhm.
Okay, gonna take 800 seconds. That's a long time. Okay, I mean, there's, well, so 60 seconds in a minute. Yeah, it's gonna be, what are we looking at there, like,
It's like 13.
13 minutes, yeah.
Yeah.
yeah. It's a long time to crawl 200 meters, but they're not very fast. They can swim real fast, but they're not so fast when they're crawling. Okay, everybody all right with that? All right, we'll do, you know what, we'll do this, we got time. Now, this is a two-part, okay? So, and it's vector. I feel like we're not gonna get into this one enough. No, we'll do this one, we'll start tomorrow with this one. Okay, reminder, plant transport labs, 8:30 tomorrow morning. Okay, make sure that they are ready, turned in, okay, for 8:30 a.m. Hint, hint, you have a little bit of time right now, you can work on them if you're not done.